I will then talk about the next part of Chapter 8. Sound good? You guys have a nice weekend? Yeah? You guys do anything fun? Cool. Me too. Unfortunately. All right. So, let me just take an example right now. What if, I'm just going to take one of the ones that you guys had to do. This is just out of section 8.6. And this is IQs. I'm not a fan of this question, but it works number-wise. And what this says is the IQs of students at Wilson Elementary School were measured recently and found to be normally distributed. And they say with a mean of 100 and a standard deviation of 15. Okay? So, I want to find a couple probabilities, and then I would like to do an inverse norm. What if we want to find the probability a randomly selected student, this is review from last week, you guys, last Friday, so this is nothing new, had an IQ, I don't know, what do you want to say, above 120? Or, let me say, had an IQ of 120 or higher. Now, for those of you guys with those sweet calculators, yeah, you would just get your normal CDF and do the lower upper mean standard deviation. For those of you guys with a calculator like me, we are cool too. So, check it out. And Hannah, tell me if you get this too. Okay? So, what you do is you hit normal CDF. Are you guys ready? We want to do 120 or higher. What is my lower? 120. Put a comma. What do we put for our upper? 10 to the 99. What's my mean? 100. What's my standard deviation? 15. Close your parentheses. Oh my God, you guys, isn't that beautiful? You got it? Sweet. What if we want to find the probability that a randomly selected student has an IQ between 120 and 150? What would we do for this guy? Well, same darn thing, but now we have our lower and our upper given. Right? What's our lower? 120. What's our upper? 150. My mean is the same. My standard deviation is the same. And so is my probability symbol. You guys okay? Let's do one more of these. How about less than 70? Okay. What's our lower? I mean, technically it's 0, right? You're not going to get an IQ of less than 0. But we could put negative 10 to the 99. What's the upper? 70. What's my mean? What's my standard deviation? Come on, you guys, isn't this awesome? all day? There we go, 2%. Who is a calculator like mine? Aren't you guys psyched? With the inverse norm, yeah, then I went into Snoopy and did this. Like, oh my God, I'm so mad. Okay. So, same problem. Let's find the minimum IQ that would place someone in the top, I don't know, 1% of all such students. Who would walk around and be like, I'm in the top 1%? Ow. I once saw a bumper sticker, my kid put up your honor students. I always thought that was funny. You know how people have like their proud parents with an honor. Okay, are you guys ready? No matter who you are and what calculator you have your inverse norm. And no matter which situation you're in, it's always the area to the left. If you're in the top 1%, what is the area to the left? 0.99. Now what we do is just put a comma, and we put in our mean and our standard deviation. So, check it out. 0.99, comma 100, comma 15. Close it up. They need an IQ of about 135. Yeah.
So when is there like any like trick, when you use the inverse norm over the
Yeah, you use the normal CDF when you want to find the probability. Okay? Because that's when you're finding the probability or the area under the curve. You use the inverse norm when you're given the area and want to find a number that corresponds to the particular problem you're working with. Does that make sense? Okay, so essentially if you're asked to find, if you're dealing with a normal distribution and you want to find the probability, you do the normal CDF. Okay? If you want to find some X value, in other words, VIQ, or, remember we were playing with factory workers' wages or something like that. You want to find some X value, that's when you're going to use your inverse norm. Isn't that cool? Don't you guys feel better? I do too, about that. All right, are you ready? So, now what we're going to do is cover the last thing in this section, okay? And what we're going to be talking about is a mouthful. It's called the normal approximation to the binomial distribution. You concur it's a mouthful? Now, one reasonable question might be, how do you know when to use the normal approximation to the binomial distribution? Well, the problem on your test will say, we'll have to indicate it. It'll say something to the effect of, using your knowledge of the normal approximation to the binomial distribution, blah, 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 blah. Okay? That's a really good indicator. So, what is the situation here? Well, it turns out if our value of n binomial distribution, we can use the normal approximation to do some computations. And they actually turn out to be quite accurate. Now, what does it mean for n to be large enough? There are rules that say what values of n will work in various situations. That's nothing that you guys need to worry yourselves about, okay? The binomial is one type of distribution. Your normal is another type of distribution. They're actually very different types of distributions. We're not going to go away into the background information of this. Those of you guys going on into statistics can learn that. That's not as relevant for this course. But essentially, your binomial distribution is called a discrete distribution. In other words, you can compute the probability at any particular value. Whereas your normal approximation is not. It's called a continuous distribution. So you only find probabilities within regions. You never find a probability at an exact number. Okay? So you might have noticed when we've been computing our probabilities with our normal distribution, it's always been find the probability that it's less than this or greater than this or between this. It's never been at an exact value. Okay? Because that's not how your normal distribution works. So if you're wanting to find that range in a binomial situation for a large enough sample size, you can use the normal approximation. Let me show you how we do it, and let me show you how it goes. There's one funky thing that goes on, and it's a little fudge factor we have to talk about. But when you're dealing with the normal approximation to the binomial distribution, and I even wrote it on your test at the request of someone in my 9 o'clock class, I even give you a hint, bump 25. You have to know which way to bump, and you guys are probably like, what the heck are you talking about? Hold on a second. Okay? So, let me put down an example and let's play with it. Suppose 6% of cereal boxes are overfilled. And there is a run of 500 cereal boxes. Okay? Let's stop right here. Will you guys grant me that this is a binomial situation? Why is it a binomial situation? Well, I think the biggest alert is that a general probability or percentage is given to us. Okay? That's usually a good way to tell. But notice, okay, you have independent trials. We have many trials, 500 of them. Presumably each time a machine fills a cereal box, whether or not it's overfilled is independent of another time. Either it's overfilled or it's not overfilled. Okay? So this is a classic binomial situation. Okay? Now, we're going to want to find probabilities here. What if I want us to find the probability that at least 275 are overfilled? Okay? Now, what I would say on a test is using the normal approximation, etc., etc. But let's look at this, you guys. If I want to find the probability that at least 275 cereal boxes are overfilled, do you guys agree that means 275 or 276 all the way up to 500? Do you want to do that many binomials? No. Is the complement any better? No. I mean, it's still 0 through 274. Okay? So, here is the scenario. Part A. Find your mean and your standard deviation. Can we find our mean and our standard deviation of a binomial distribution with relative ease? Yes. Do you guys remember the formulas? Some people do. Remember, the formula is n times p, and this is n times p times 1 minus p. You take the square root of the whole thing. Okay? Now, if I didn't tell you this was binomial, and I just gave you the scenario up to here, in other words, I said, hey guys, 6% of cereal boxes are overfilled, there's a run of 500, find the mean, you would know it's binomial because this is the only information you're actually given. How else would you know it's binomial? Because I'm asking you to compute the standard deviation, aren't I? And I already told you that the only time I'd ask you to find one of those lucky standard deviations was on that quiz. Okay? So, we can definitely find our mean and our standard deviation. In this case, how would you find your mean? What would you multiply? Good, you would take n, which is 500, times 0.06, which is p, and here our mean is equal to 30. That's about the expected number of overfilled cereal boxes that we're looking at. You all okay with that? Now, let's find our standard deviation. Okay, what is my n? That's 500. My p was 0.06. Okay, you guys, 1 minus p. What is 1 minus 0.06? 0.94. Remember, these guys have to add up to 1. You with me there? All right. So, let's take that times 0.94, and then we'll take our square root, and we get 5.31. Guys, with me here? Okay? Now that we've found our mean and our standard deviation, what I will say is, using your knowledge of the normal approximation to the binomial, and we wanted to find the probability that what? At least 275 are overfilled. Okay. This is where your bump of 0.5 comes in. You need to think about this, you guys, and you need to read the English very carefully. Because we're adapting one type of distribution to another, we need a little fudge factor, essentially. Do you guys agree that if I want at least 275, I want 275 or greater? Okay? The first question you have to ask yourself is, do we want to count this 275? By the way it's worded, are we interested in 275? Yes, we are. Okay? Since we're interested in 275, I need a little fudge factor. It's kind of like my little cushioning here, to be sure I count it. So what you do then is you bump 0.5 to the left. In other words, for your normal CDF, I claim the lower is 274.5. Okay, that gave me my little leeway here to count that 275. For my upper, well, what's the maximum number of cereal boxes we have? 500. Our mean we found to be what? 30. And our standard deviation we found to be 5.31. If this is confusing, don't sweat it, you guys. This is one example. We've got a lot of time to do more. All right. So what would this look like? We would put in 274.5, comma 500, and then we have 30 and 5.31. This isn't bloody likely. As I said, probability is 0. All right. Let me take another example, and this one we're going to play with a lot of different scenarios. Suppose a marksman chance of hitting a target is 60%. And it says assume that the shots are independent of each other. I'm going to change this a little bit. Suppose he fires, I don't know, how many shots?
105.
No, the end's got to be big. 200 shots. Is it okay? So, suppose he fires 200 shots. Okay? Part A. Let's find the expected number of targets he hits. And I'm not being sexist. I'll make the next one a sheet. How do you find the expected number? Isn't it n times p? So we can expect that this fellow is going to hit the target 120 times. Guys, with me this far? All right. What if I want you to find the standard deviation? Can we do that? Totally. And you guys, just think about this from a basic test-taking strategy. If I tell you the only time you'll ever have to find a standard deviation on your exam is in a binomial situation, you can make that link. Okay? So, the standard deviation is the square root of n times p. If p is 0.6, what is 1 minus p? 0.4. Is everybody with me this far? Yeah? All right, so let's compute it. We have 200 times 0.6 times 0.4, and we get 6.93. Okay? Any questions this far? Yes?
And it's only binomial distribution where the expected value is n, right?
Yes. Yes. Otherwise, you have to have that probability distribution table. Yeah. Any other questions? Okay. Let's find some probabilities. Let us first find the probability. Find the probability of his hitting the target. Let's do this. Between I don't know, how about 130 and 180 times inclusive. This will really help us with the 0.5. And you guys, by the way, if you bump 0.5 in the wrong direction on a test, it's not like it's going to hurt you that bad. I mean, you lose a point maybe, so. Okay? Now, here we want to find the probability of this hitting a target between 130 and 180 times inclusive. What do I mean by inclusive? I want to include these endpoints. In other words, I want to talk about the 130 and I want to talk about the 180. Now, if I'm using my normal approximation here, we're really thankful that we found our mean and our standard deviation, aren't we? Because we are going to put in normal CDF. All right, you guys, if I want to count that 130 and I'm getting bigger, what am I going to bump him to? It's always a bump of 0.5. Good, 129.5. Do you guys agree if I go down to 129.5, I cushion him in? If I want to include 180, but I need to cushion him in, what am I going to have for my upper? 180.5. And then I put in my mean and my standard deviation. Does that make sense? Kind of, sort of, at least at this point? So, let's see what we get. You hit second bars, normal CDF. We have 129.5, comma, 180.5, and then 120, and then 6.93. And we have about 8.5 or 9%. What if I want to find the probability of him hitting the target? Let's just set these up. At least 170 times. And then let's set this one up. At most, who cares? 150. What I want to be sure you guys can do is figure out the bumps. Okay, so if I want at least 170 times, doesn't that mean 170 or more? Okay, everybody with me there? Do I want to count that 170? Yes. So if I'm starting at 170 and I want to go higher, which way will I have to cushion him? To the left a little bit. Good. So I would do 169.5, and then we max out at 200, and then I put in my mean and my standard deviation. Does that make sense? Now, for my next one, I want at most 150. So I want 150 or less than that. I'm drawing this on the number line so it maybe is a little clearer which way to buffer. Okay, you always buffer in the opposite direction if you want to count that point. So, in this case, my lower would be 0, wouldn't it? Don't worry, if you put -10 to the 99th out of habit, that's fine. Okay, what would be my upper now? 150.5, and then we put in our mean and our standard deviation. Does that make sense? Do you guys want me to go through and compute this? Or are you guys okay computing it? You want to see one more example? Okay, now let's talk about a a female basketball player. I'm so used. Okay. Oh my gosh. Okay, a basketball player has a 75% chance of making a free throw. That's pretty sweet. And it says assume that the throws are independent of each other. Suppose, well, I'll just write it as it is. What is the probability of her making 100 or more free throws in a trial of 120? God, shooting 120 baskets right in a row. This is the way it's worded in your textbook. I'll now write out Warren's version. Find the mean and the standard deviation of her number of free throws. Can we do this? Absolutely. To find our mean, it's n. What is n? 120 times p, which is 0.75. Don't you get 90? You guys with me there? Now we can find our standard deviation, and that's the square root of n times p. Hey guys, if p is 0.75, what's 1 minus p? 0.25. This one I can't do in my head. So let's see what it is. It's the square root of 120 times 0.75 times 0.25, and we get 4.74. Any questions this far? All right. You good this far? Cool. Part B. Using your knowledge of the normal approximation to the binomial distribution, let's find the probability of her making 100 or more free throws. Normal CDF. Am I interested in the 100? Yes. Since I'm going greater, don't I buffer it to the left then? So what will I put in for my lower? 99.5. For my upper, well, she's shooting 120 throws. My mean is 90, and my standard deviation is 4.74. And in case anybody really cares, let's see what we get. 99.5, and then I want to just change the wording of this ever so slightly. And we get about 2%. We're getting teeny percentages today, aren't we? It's a Monday. Okay, can I reword this one slightly? Because it'll change our bumping to 0.5. Everyone ready? You guys have the Monday thing happening? you guys just burnt out? You look at a lot of you guys do. I understand. What if instead I want to find the probability of her making more than 100 free throws? This just changes it ever so slightly. We still have that normal CDF. We're still maxing out 120, and our mean and our standard deviation is still the same. But do you guys see how this is worded slightly different? Cool, thank you. Right? Because I'm interested in now in more than 100. Am I interested in 100? No. What would be the smallest number I'm actually interested in? 101, right? So, if I want more than 100, but I want to include 101, what would I bump to now? 100.5. Good job. And you'll see what a trivial difference it really makes. Let's compute it just to see. And what do we have? 100.5, 120, 90, 4.74. Let's see the difference it makes. See, it makes a slight difference, but not a huge one. I guess my point is read carefully, words are important.